Solving trigonometric equations. This video will help you find all solutions of a trigonometric equation, solve equations with multiple angles, solve trigonometric equations in quadratic form, use factoring to separate different functions in trigonometric equations, use identities to solve trigonometric equations, and use a calculator to solve trigonometric equations. Trigonometric equations and their solutions. A trigonometric equation is an equation that contains a trigonometric expression with a variable. For example, such as here we have sine of x. If that expression was contained in an equation and we're asked to solve that, that's a trigonometric equation. The values that satisfy such an equation are the solutions, and remember, the trig functions are cyclical, so we can have lots of solutions here. So then, and there also are trigonometric equations that have no solution. When an equation includes multiple angles, the period of the function plays an important role in ensuring that we do not leave out any solutions. As discussed, with these trig functions, they're cyclical and periodic, so we need to make sure we include all the solutions. A lot of times there'll be boundaries on the areas that we're looking for solutions. Most of the time 0 to 2 pi. But sometimes those boundaries could be different, and sometimes there'll be no boundaries at all. So we want to make sure once we solve the trigonometric equation, we pay close attention to the boundaries and make sure we get all of the solutions that are inside of our boundaries. So here are our strategies, and we have 4 different strategies, and these are kind of strategies you're going to want to keep in mind. If you're taking notes now, it would be a great time to write down these strategies. We're going to look at them one at a time here. The first one we're going to take a look at is to solve a trig equation that contains just a single trig function. All we want to do is isolate the function to one side of the equation. It's a lot like solving when we had, for example, a regular standard linear equation and we're looking for a solution for x or something like that. So very similar to that. So let's take a look at an example now where we have just a single trig function involved in our equation. And so now a single trig function doesn't mean we just have one of these trig functions in there. It means we just have one type. And it's linear, meaning we don't have any squareds on it. So here we go. Let's take a look at our first example here. 5 sine of x equals 3 sine of x plus the square root of 3. So this is really similar to solving a problem like this. 5x equals 3x plus the square root of 3. Very similar to that. So what we want to do is we just want to isolate, in this case, the sine of x, just like over here we would want to isolate x. So first thing we're going to do, you can see I'm subtracting 3x from both sides to get all my variable terms to one side. When we do that, we'll have 2 sine of x equals the square root of 3, and then divide both sides by 2. And we see that the sine of x now is equal to 3 pi over 2. Now, solutions on this interval, notice we're restricting it just to this, there are no restrictions on this interval. So notice up here, if there were going to be restrictions, or boundaries on our range, our domain here, they would have listed it right here. And there aren't any, so we want to find every possible solution to this equation going round and round and round our circle. Okay, but the first thing we do is we're first just going to take a look here at solutions for the equation between 0 and 2 pi. So if we think about our unit circle here, and it's always coming back to this unit circle, so make sure you're getting a handle on this. So we're almost at the square root of 3 over 2. We're almost at the square root of 4 over 2, which is 1. So we're right here. Here's a location where the y coordinate is the square root of 3 over 2. And here is the coordinate. Both of those are almost going to be 1 right there, and both positive. So we get these two solutions. Here's pi over 3. And this is 2 pi over 3. And you can see that's where we're getting these solutions from right there. That's where the sine of x is equal to the square root of 3 over 2. If we travel around the circle one time, between 0 and 2 pi, those are the only places that that solution is going to come up. Now, however, every time we travel back around this circle, we are going to run into those two solutions again. And so notice every time we travel 2 pi, which is a distance all the way around the circle, we'll be back at this solution. Same thing here. Travel around 2 pi. Every time we do that, we'll be back at this solution. So you can see when we list our solutions in our final answer here, we say, okay, pi over 3 plus 2n pi every time we travel around the circle, 2 pi times, we're going to come up with a solution. And n, remember, is just our counting numbers, 1, 2, 3, 4, so on. And that will indicate every time we're traveling around the circle. And then same thing here, 2 pi over 3 plus 2n pi. So we want to make sure, if we don't see any boundaries on our domain, our input values here, we want to make sure we have an answer like this to include all potential solutions as we keep traveling around that circle. Okay, let's look at the second strategy now. To solve for multiple angles, set the expression inside the trig function equal to the solution plus n times the period of the trig function. Now this is a lot to kind of take in, and I think when we look at an example, it'll make a lot more sense. But we're going to take what is inside the trig function and set it equal to what would normally be the solution plus n times the period, just like we did n times the period last time. All right, let's take a look at an example here so you can see what we're talking about. So here's our equation we're asked to solve. Tangent of 2x is just equal to the square root of 3. And this time, notice we're putting a boundary on our domain. We're only looking at solutions between 0 and 2 pi, and we're not going to include 2 pi as part of our solution here. So what we ask ourselves first before we go to solve this is we say, okay, tangent of what would give us the square root of 3? That's how we start. So we kind of don't worry about that 2x at first. We just kind of think about what angle value do I plug into the tangent to come up with this square root of 3? And the answer is pi over 3. And you can see that right here. When I put pi over 3 into the tangent function, I get the square root of 3. So what that tells me then is that in order for this trig function to work, this 2x is going to have to be equal to pi over 3. And so that's what I'm writing right down here. 2x has to be equal to pi over 3. Now the other thing we want to include here is that since the period of the tangent is pi, every time we add a pi to this, we're also going to get another solution. So there's more than just one location here as we're traveling around this circle. So we take the inside of a trig function, which is 2x. We set it equal to what would give us that answer, pi over 3, plus n times the period of our trig function. Since this is the tangent, the period is pi, so we're going to go n times pi. Had this been a sine or cosine function, we would have n times 2 pi here. Now what we do once we get this little mini equation set up is we solve this equation for x, which would have us then dividing by 2 or multiplying everything through by a half. I think it's easier here since we have a fraction to multiply by a half. So I multiply this by a half, I get x. Pi over 3, when I multiply that times a half, I get pi over 6, and n pi, I get n pi over 2. So what I've done here is just taken this whole equation and multiplied times 1/2 to solve for x, but I got to make sure I multiply every one of these terms in the equation. So this now is going to give us our solutions to this equation, because notice this 2x up here in my equation is going to speed the tangent period up. So we are going to have twice as many solutions now in this period between 0 and 2 pi that we normally would. Well, this solving this little mini equation has taken care of that for us. We get pi over 6 plus n pi over 2, and what we're going to do now is we're just going to keep adding. We're going to evaluate this for n equals 1, n equals 2, n equals 3. Keep evaluating for the n's until we get outside of our domain here, which is 2 pi. So let's take a look at what that looks like. So when n is equal to 1, remember our first solution here is when n is equal to 0. So the first thing we do is we look at when n is equal to 0, we're going to get the answer of just this, pi over 6. That's our first solution. Now let's get our second solution. So when n is going to be equal to 1, what we're going to be doing then, putting a 1 in there, we're just going to be adding another pi over 2 here. And so you can see this, pi over 6 plus pi over 2. Now we're going to get a common denominator to add these two fractions together. pi over 6 plus 3 pi over 6 gives us 4 pi over 6, and when we simplify that, that gives us 2 pi over 3. So there is now our second answer. And notice we haven't gone outside of our boundaries here yet. We haven't gone past 2 pi. This is not even pi yet, so we're still going to keep going. Now we're going to look at when n is equal to 2. Alright, when n is equal to 2, we plug that guy in there, add 2 pi over 2, which is the same as 6 pi over 6. We get our third solution here, 7 pi over 6. Then we're going to look at n is equal to 3. When we plug that into our little mini equation here, we're going to get 5 pi over 3. Let me show you now when we put n is equal to 4, because what we're going to do is we're going to keep going until we get to 2 pi or go past 2 pi. Well, we're still short of 2 pi. Remember, 6 pi over 3 would be 2 pi. So let's look at n equals 4. So what we would do then is we'd have pi over 6 plus 4 times pi over 2. When I put 4 in there for n. And so what this is going to be, this is going to equal pi over 6. And this is really 2 pi. Do you see that? If I simplify that. So if I take 2 pi and add it to pi over 6, now I've gone further than 2 pi. So this is going to be outside of domain. So I don't have to evaluate this one. But let's say we hadn't noticed that yet. And we said, okay, we get a common denominator here of 6. That would be 12 pi over 6. And I'd add these together and I'd get 13 pi over 6. And now you would take a look and say, well, have I gone past 2 pi or have I gone higher than 2 pi? And I have, because 12 pi over 6 is 2 pi. So we would know that this answer is not going to be included. We could stop right here at 5 pi over 3. Now what we want to do is list all of our solutions here. So here was when n was equal to 0, 1, 2, 3. Those are all my solutions now. All right, let's take a look now at a practice problem here to practice solving for multiple angles. So here's our equation here. Sine of 2x minus 1/2 equals 0. So this one isn't quite solved. And in order for me to explain this and get us set up here, let's solve it. So the first thing we would do is we want to isolate sine of 2x. So we're going to add 1/2 to both sides. So then we have this. Sine of 2x is equal to 1/2. Now, we want to figure out what angle, if we take the sine of this mystery angle, it gives us 1/2. Well, there are two locations on our trig circle between 0 and 2 pi where that's going to happen. So in this practice problem, it's a little bit different than the last one. We're going to find two locations, and then we're going to set up two of these mini locations here. So think about the unit circle. Think about where the sine of x is going to be equal to 1/2. Find those two locations. Then set up two of these equations here. And now, since our period for the sine of x is 2 pi, we want to have, before we solve this, we want to have plus 2n pi, or n times 2 pi here in both of those locations. Let's go ahead and pause your video player now and give this a shot. Okay, as discussed, if we were working this problem from the beginning, we'd say, okay, first thing I got to do is I got to isolate this sine of 2x. And so I'd add 1/2 to both sides, get it isolated, then I'd say, okay, at what point sine of what angle gives us 1/2? Well, that happens in two spots. It happens right here. Remember, sine is our y coordinates. It starts out at 0. Excuse me. Starts out at 0, travels up to 1/2 right here. It also, our y coordinate is 1/2 over there. So those are the two locations. So this angle here is just going to be pi over 6. So when I travel up pi over 6, it's going to be my first one, plus then n times 2 pi, because that's my period here. Because we're dealing with the sine, the period is 2 pi, so I take n times 2 pi. Now let's talk about this location. So this location is almost pi around, which would be 6 pi over 6. So this is 5 pi over 6. And again, plus n times 2 pi. And now I want to solve each of these mini equations. So I'm going to multiply everything through by half to get my solutions. So that's going to give me x, and then that's going to give me pi over 12. And then this is going to give me n times 2 pi over 2, which means those 2's are just going to divide out for me. So my equation would be pi over 12 plus n pi. All right, same thing here. Since I had 2 solutions, I need 2 of these equations. Go through and multiply everything by a half, and I'll get x is equal to 5 pi over 12. And then here again, those 2's are going to divide out, and I'll have plus n pi. Okay, now, so I found 2 of my solutions, and I'm looking at my solution set here. I'll write my solution set off to the side. And a lot of times we use brackets or braces here to enter our solutions. So pi over 12 was 1. And we know that 5 pi over 12 was the second. Now let's start adding multiples of pi here on the ends to see what we get. So if I add n equals 1 here, that would add a pi to this. So my next solution would be, if n equals 1, it would be this, x equals pi over 12 plus 1 pi. Well, let's make that, turn that into 12s so I can add it to that fraction. 1 pi is 12 pi over 12. And so that's going to give me 13 pi over 12. So let's put that over here, 13 pi over 12. Because I still have not gone past 2 pi yet. That's just a little bit more than 1 pi. It's still in my boundary here, so that's good. All right, let's say when n equals 2 here. So then I'd have pi over 12. But now I'd have 2 pi there, so pi over 12 plus 2 pi. That isn't going to work because if I take 2 pi and add a little bit more to it, now I've gone outside of my boundaries here. So that's not going to work. So n equals 2 is not a solution. Let's come back and check this guy here. So we've already got a first solution, 5 pi over 12. Let's try when n is equal to 1. So when n is equal to 1, I'll have 5 pi over 12 plus, let's change that 1 pi into 12. So again, that'd be 12 pi over 12. Well, let's see. So that's going to be 17 pi over 12. Oh, let's write this right up here. That was 17 pi over 12. That's still within 2 pi. It'd have to be 24 pi over 12 for it to be 2 pi exactly. So that's still within our boundary set. So then 17 pi over 12. If I tried another one here, if I tried n equals 2, again, I'd be adding 2 pi to this, and it'd go too far. It'd go outside of my boundary set. So there are my solutions right there. Okay, let's take a look at another strategy here. And so now we're going to be solving a quadratic. Those were cases where the last problems we looked at were cases where our trig functions were to the first power. Now we're going to be solving ones where we have trig functions to the second power. Quadratics will have squareds in them. And so there's 2 kind of strategies we use here. The first is if we just have a single squared term and we can isolate it, and there aren't any other trig functions in there, we isolate the squared term and then take the square root of both sides to solve for it. Now, if we have, like for example, a sine squared and then a sine to the first power, and we have a quadratic that looks like that, then our strategy is going to be to factor. Okay, so as discussed now, we're going to practice this, solving this trig function that's quadratic. Notice we just have cosine squared x. So factoring is not going to be our strategy here. We're just going to isolate and then take the square root of both sides to solve for this. So go ahead, pause your video player now, and make sure you find all of the answers between 0 and 2 pi. Okay, so let's take a look at the solution here. I think I have it worked out in the next slide. Okay, so here we are taking a look over here. First thing I'm going to do is add 3 to both sides. and then divide by 4, and I get the cosine squared of x is equal to 3/4. Now I'm going to take the square root of both sides, which will give me the cosine of x, and then remember, whenever we take the square root of this, we'll have plus or minus the square root of 3/4, and then we can simplify this 4. We take the square root of 4, which is 2. So here are my solutions now. We get plus or minus the square root of 3/2. We are looking now for cosine answers where we get plus or minus the square root of 3/2. So let's take a look at our unit circle here. Cosine of x, square root of 3/2 is almost where it's 1. So here I would get this positive square root of 3/2. Here I would get the negative square root of 3/2. Also here I would get negative square root of 3/2. And right there I would get positive square root of 3/2. So we've got 4 of these locations. The first one here being at pi over 6, almost all the way around to 6 pi over 6 here. This is going to be 5 pi over 6. Then I would be at 6 pi over 6. Here I would be at 7 pi over 6. And then all the way around, if I went all the way around, and again counting by these pi over 6 because that's my reference angle here, all the way around would be 12 pi over 6. So here I'm going to be just 1 pi over 6 short of that. So this angle here would be 11 pi over 6. And so that's how you find these solutions. You just go look around, think about your unit circle, and find them all. So we've got 4 of them. Pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. And you could say this, you could write it this way, you know, the solutions to this equation are this, or we could put braces around these, and we wouldn't have to include this and in there. So that was the first one where we had just a single squared term in there. Now let's take a look at one where we're going to need to factor to solve this. Okay, so we're going to practice this one. Again, now notice we have more than one sine of x function here. So if we had one, we'd be back to our solving our linear. But here we're going to want to factor this one to solve it. So what you want to do is get the sine of x on both sides, use some factoring, and then solve your little mini equations there. Go ahead and pause your video player and give this a shot. When we get it correct, here are our solutions down here. 0, pi over 4 pi, and 5 pi over 4. So see if you can come up with those answers. Okay, so I didn't mention this, but hopefully you didn't make this mistake. So sometimes the go-to mistake to make here, and it's really easy to make, is say, hey, look, I'm going to isolate tangent of x by just dividing both sides by sine of x. This could be a solution. Look, if I divide by sine of x, divide by sine of x, it would just give me tangent of x is equal to 1. Man, that would be super easy to do. And I'm with you, that would be super easy to do. The problem is this, we can't do that because sine of x on this interval between 0 and 2 pi is actually equal to 0 at times. So essentially, if I divide by this sine of x on this interval, we're going to essentially be dividing by 0 here, which we can't do. If we solved it this way, we would get some of the solutions, but not all of the solutions. That's how it would kind of end up as a problem in our answer. So basically, we do this. We don't ever divide by trig functions if we end up having a 0 on the interval that we're evaluating, and we do here. So this is not going to be the correct strategy for this. It would give us one of the answers, but it wouldn't give us all of the answers here. So let's not do that. If you did that, that's okay. It's a common go-to mistake. Go ahead, if you did that, go ahead and pause your video player now, get sine of x over here, and use factoring to solve this. Alright, so what I want to do first is I want to subtract sine of x from both sides. So I get 0 on one side, and then I have sine of x. Then I'd have sine of x, tangent of x, minus sine of x. Now I want to factor out a sine of x here. It's a common factor in both of those terms. And so I'll get tangent of x minus 1 inside of there, and sine of x on the outside. Once I've got this factored now, I want to solve each of these little mini equations separately. So I'm asking myself, when would the sine of x be equal to 0, because if I take 0 times this, it'll work, right? So that's one equation I want to find out. And the other one is this. Tangent of x minus 1 equals 0. Well, let's think about this. Sine of x equals 0. If we look at our unit circle here, our y coordinates when they're 0, they're here, and here is when my sine of x is going to be equal to 0. Well, this is at 0 itself. So one of my angles here would be 0, and the other time I get to be 0 is over here at pi. So there would be my two answers there. Now I want to solve this little mini equation here. Tangent of x minus 1, so I'd add 1 to both sides. And I say, okay, well, whenever the tangent of x is equal to 1, that will also be a solution. So I want to know where the tangent of x is going to be equal to positive 1. Well, remember, tangent of x is sine over cosine. So I'm thinking, when does sine of x and cosine of x equal each other? Because if sine of x and cosine of x are the same, that's going to be equal to 1. Well, there's two locations here. Well, there's more than two locations where they're going to be equal, but where they're going to be equal and give us a positive output value. One is right here, right at this 45-degree angle, or pi over 4. That's where both the y coordinates and the x coordinates are the same, right? As I travel around the circle, this is right where they're the same, and that's when they're the square root of 2 over 2. They're both root 2 over 2 there, and that is at an angle of pi over 4. So that would be positive. Over here they'd be the same, but my x-coordinate, notice, would be negative, so that would give us a negative 1 there. But down here, when they're both negative, this would be another location where they would both be negative, and when I take a negative divided by a negative, it would still give me a positive. So let's see, this would be at pi plus pi over 4. That would be at 5 pi over 4 for that angle. So we've got two locations here. It would give us a negative result for our tangent, so we don't want that. So here are my two locations. So this is going to happen at pi over 4 and 5 pi over 4. So I've got 4 solutions here. And you can list them this way: 0, pi, pi over 4, 5 pi over 4. But a lot of times you'll see people organize them from least to greatest. So that would be 0, then pi over 4, then pi, and then 5 pi over 4 for our solution set there. Okay, so now we're going to take another practice problem here, and here we're going to use an identity to solve it. And if we look at our equation here, cosine of 2x plus sine of x is equal to 1. If I didn't have this sine of x in here, I could use our multiple angles technique like we did already. But since I have this sine of x in here, that's going to cause a lot of problems for me. What I want to do is I want to get the same, since I have more than one of these guys here, I want to get them all to be the same trig function. If I can get them all to be the same trig function, then I can use a factoring strategy, or I might be able to use an isolation strategy where I get them all together on one side of the equation. But I can't do that if I have different trig functions in there, where I can't factor, and especially now when I have this cosine of 2x in there. So what I want to do now is I want to look on my formula sheet at different identities I could use to make a substitution to get all of these trig functions the same. And so notice this is a double angle. Cosine of 2x is a double angle. So I'd look on my formula sheet, find all my double angle formulas, and here they are right here for the cosine of 2x. I have 3 of them. The reason I have 3 of them is because it's handy to have more of these identities, because I can pick the one that I want. So why don't you look through the possible identities here for the cosine of 2x. Pick the one that's going to be the most advantageous here, and then go ahead and solve this equation once you make that substitution. If we get it correct, here are the answers we're looking for right there. So go ahead, pause your video player now and give this a shot. All right, so let's see. Here are my double angle formulas. Cosine squared minus sine squared. Well, that might help, but then I'd still have different types of trig functions in the same equation, which could be tricky. Same with this 2 cosine squared of x. I'd have sine of x and cosine of x in there, not as easy, but this guy right here is going to be the best, because then I'd have sine of x and then 1 minus 2 sine x squared. That's all the same trig functions. That's going to be my strategy here. So I'm replacing this cosine 2x with this guy right there. So I'm going to have 1 minus 2 sine squared of x plus sine of x is equal to 0. So I want to factor this guy. First, let's get this in nice descending order. So it would be negative 2 sine squared of x plus sine of x plus 1 is equal to 0. I'm not used to usually factoring with this negative out front. You could absolutely do it, no problem. I like to factor with a positive term out front, and with 0 on this side, it's really easy to do. All I'm going to do is multiply both sides by negative 1, and it'll make a positive leading term here. So then if I multiply that by negative 1, it'd be 2 sine squared of x minus now sine of x minus 1 equals 0. These two equations will have exactly the same solution. I'm used to factoring this guy, so I'm going to leave it like that. And again, just by multiplying both sides by negative 1. So when I look to factor this is going to be 2 sine of x. Last term is negative, so I want plus minus. I also want to have more negatives in the end, so I'm going to put the minus over here so that when I multiply this times a negative, it will give me a nice big negative value there. So plus here, and then I guess maybe just 1 and 1. Let's see if that works. So let's see, 2 sine of x times sine of x gives me 2 sine of x squared. This would give me, outsides would be negative 2 sine of x, insides would be positive sine of x. That gives me negative 1 sine of x, and then positive 1 times negative 1 gives me negative 1. So that works. So there's the factoring. So now I want to solve each of these equations and figure out when they're going to be equal to 0. So 2 sine of x plus 1 equals 0. When I solve that guy for the sine of x, I'd subtract 1 and then divide by 2. So sine of x is equal to negative 1/2. Here, when sine of x minus 1 equals 0, that would be when sine of x is equal to 1. All right, so let's talk about now these angles where that happens. So let's look at our unit circle here. First, let's talk about when sine of x is equal to negative 1/2. So here's where it's 0. Here's where it's 0. Negative 1/2 is going to be right there and right there. Think about my y coordinates starting at 0. My very first jump, either going up or down, is to 1/2. Up would be positive 1/2. Down would be negative 1/2. And then same thing over here. Here's where sine is 0. Down 1 unit there to our first angle there. And those are jumps of pi over 6. So my reference angle here is pi over 6. So this is going to be, if I go all the way around the circle here, let's talk about this one. This would be at pi plus pi over 6. So pi plus pi over 6 to get to that location. Well, this is 6 pi over 6 plus pi over 6. That's going to be 7 pi over 6 for that location. This location is almost all the way around. It's pi over 6 short of going all the way around the circle. So that is going to be 11 pi over 6. And just like I talked about, that's all the way around the circle would be 2 pi. But then we're going to drop back pi over 6. If you couldn't follow me there, this is 12 pi over 6. Pi over 6, that's how I got that 11 pi over 6 in my head. Okay, so 11 pi over 6 is my other one. That's 2 of my answers. Now, when is the sine of x going to be equal to 1? Well, that's only in one location. Here it's sine of x, my y coordinates at 0. This is the only spot where it's at 1, and that's pi over 2. So pi over 2 for that guy, and we said here 7 pi over 6 and 11 pi over 6. And then we would go ahead and list those solutions up here. All together, pi over 2, 7 pi over 6, and 11 pi over 6. Last strategy here is to solve using a calculator. And so a lot of times we're going to have angles and values that are not on our unit circle. And when that happens, we're going to use inverse trig functions to get our first solution. And then what we do after we get that first solution is we take that first solution and look on our unit circle and make sure that we find any other places where that solution can appear. Okay? So one thing that I will say when we're solving for these trig functions where we're using our calculator, we are staying in radians here unless otherwise specified. So if we're going to get any sort of answers in degrees, it will be part of our question. It will say, go ahead and find this solution in degrees. If it doesn't say, then it's understood that we're working in radians. So here in this video, we're going to be just working in radians. So you want to make sure that your calculator is set to radians, or else you'll be getting some crazy, bizarre answers here that won't make any sense. So let's take a look at an example here. So this is what happens. So we've got this trigonometric equation. Tangent of x is equal to 3.144. And we want to find the angle now correct to 4 decimal places, and we're looking for this angle in radians. You can see they're specifying it because we're talking about the boundaries here, or our domain in radians. So I make sure that my calculator is set to radians, take the inverse tangent of both sides, and I get this as my angle value in radians. So there is one solution. And we've already done problems like this. The thing now is that we're looking for any other solutions on the unit circle. So if I take a look now at my unit circle here, so remember the tangent now was equal to 1 at this pi over 4, right? So we are going to be a little bit bigger than 1 here. That tells me my answer is going to be somewhere here, because remember, tangent is sine of x over cosine of x. At this pi over 4 location, sine of x and cosine of x are exactly the same, and this guy here is equal to 1. So if we want this to be a little bit bigger than 1, then we need sine of x to be a little bit bigger than cosine of x, which is happening, oh, not down there, sorry, not down there, up here, because then my y coordinate would be larger than my x coordinate. Here they're two the same. Here now my y is growing bigger, so my other answer is going to be right up here. So let's take a look now. Any other place we could come up with this answer between 0 and 2 pi. So we want an answer that's a little bit bigger than positive 1. Well, I might come over here and think, all right, well, here's pi over, this is pi over 4, pi over 4, so this is 3 pi over 4. We would think, all right, well, maybe the answer would appear here again, but not the case, because notice here my x-coordinates would be negative. So this would be negative 1.2592 right here. So that's not going to work. So that guy's not going to work. But I could find this solution down here. All right, so we've got an angle measure then down here, where my y-coordinate now would be right about there. And so what I want to do is I want to travel from this location around to this location to find my other solution. And so what we have to do is we have to think about how to travel that distance. Well, if you look at that, that's a distance of pi. And that makes sense because remember the tangent has a period of pi. So if I took this value, this angle measure right here, and I added pi to it, I would come all the way around at this other location where my answer would appear again. The answer couldn't appear in this quadrant because it would end up being negative again. So there's just going to be two answers here. So this is my first one that my calculator gave me. Now after I've done some thinking about this, to come over to this spot here, I realize I have to take this answer and add pi to it to get my second. So I would say x, it's still an approximation here because we used our calculator to get it, and I would add pi to that answer, and then that when I do that one, it would give me my second approximation here, which we can see right down there is 4.4008. Make sure when you're adding this pi here, we're trying to be as accurate as possible, so use the pi key on your calculator. Don't use 3.14 there. Go ahead and use your pi key. So you just push 1.2592 plus and then hit your pi key to get that second answer. So we're going to try the same thing now. Giving you a sine function here. So go ahead now, we're looking for all the answers between 0 and 2 pi when sine of x is equal to negative 0.23159. Sorry, 15. Make sure your calculator is set to radians here. Go ahead and use your calculator to get your first solution, and then go and look at the unit circle to figure out where your second solution is going to occur. When you're done, hit play to see how you did. Okay, so when I solve this guy, I get this angle measure, -2, 3, 3, 6. Okay, and I'm sure you got the same thing. And then you look down here at our answers and you go, well, that's not the answer. Well, it's not the answer yet, but it's going to get us the answer yet. Why isn't this one of my answers? Remember, this is the angle measure in radians. But notice it's a negative angle measure in radians. And if you look up here, we only want solutions that are between 0 and 2 pi. So we only want positive solutions here. So we're going to have to go to our unit circle to figure out how to get these positive solutions. So notice we're at a negative value here, and it's a value that's pretty close to 0. So we're going to be right here somewhere. So here's our value, let's say, traveling down this way, an angle of -0.2336. So I want to find that spot, but in a positive motion. So one of the easiest things to do here is say, hey, look, all I have to do to get this to be positive is start here at this negative angle and travel all the way around the circle and get back to it at a positive location. Well, that distance I've just traveled is 2 pi. So one way to get our first answer, which is the easiest one to see, is to add 2 pi to this. So I'm going to take this answer and add 2 pi to it so I can get back in a positive angle measure. So I take that angle plus, and then I want to take 2 pi. And so when I do that, that gives me this angle measure of 6.0496. So there's my first solution. Now let's think about when I'm going to come up with this same sine value again. Okay, the other place I can come up with this value is right over here. The y-coordinate to this location is going to be exactly the same as the y-coordinate over here, just a little bit negative, right? That's what my y-coordinate here is, just a little bit negative. In this case, if I find the right angle, I end up with this tiny little negative value here. That's going to happen over here for my y-coordinate as well. So I need to figure out now how to travel from here all the way over to here. Well, that's not going to be by adding pi. Notice if I added pi, it would take me right to here. So that's not going to work. So what I want to do, though, is if I took this and I added pi to it, it would travel all the way around here. It's not going to get me to that location. My answer is going to involve pi here. I do want to use pi. So what I want to do now is I want to come over here, pi, a distance of pi. Let's say I started at 0. Let's erase this one here. And that's not one of our solutions. So what if I did this? What if I started out at 0 here and I travel all the way around pi? That would get me to this location right here. Then if I want to go just a little bit further, I want to add this angle travel here. That's what I want to do. Well, I know that that angle travel is a distance of positive 2336. If I'm moving in this direction, I want it to be positive. Here it was negative 0.2336. But if I take this pi and add positive 2336 to it, it would get me to this spot here. So that's how I'm going to get my next answer. I'm going to say my next answer is going to be pi plus 0.2336. Add those together and it will get me to that location. And again, I want to use my pi key here. 0.2336. And that gives me this next angle of 3.3752 for my next solution. And so this is a little bit tricky. First one was a little tricky, but this one is kind of getting very tricky. So I think it just has to do with really taking a look at the unit circle and figuring out how to find these locations. You know, I knew that if I could travel here to pi and then add a little bit more, it would get me to that location. I knew the other one, if I started here and I added 2 pi to it, it would get me back around to this spot. Now, there aren't that many strategies here really with this. You know, here are kind of our strategies we do with all of these problems. It's either going to involve adding 2 pi to something, subtracting 2 pi from something, or starting at 2 pi, subtracting something away, 2 pi, adding something to it. And the same thing then happens with pi. We're either going to add pi to one of our answers, subtract pi from one of our answers, or take pi minus one of our answers, or take pi and add one of our answers. Every one of the scenarios is going to end up being one of these things. And so really it involves adding or subtracting 2 pi or pi, or starting with 2 pi or starting with pi and adding and subtracting our angles. So there really aren't that many options. So after you practice a couple of these, you'll get the hang of this and you'll get your strategies down. But always look to these guys right here to kind of help you. If you can't see how it's going to work, think about doing each one of these things. I think there's just 8 of them here that you have to try out. So just think about doing either of those things. And a lot of times you can just look at it mentally and see if it's going to end up in the right spot on the unit circle where you're trying to find. But again, getting that first picture of where our first original angle lies is important, because that's going to tell us which one of these 8 strategies over here is going to work to find these other angles.